Alright, in this notes video, I'm going to talk about um, how to write an energy equation and a tool that we're going to use, a way of representing things that we have come to call LOL diagrams. You'll see why we call them that. So this really isn't any different in terms of concept than our pie charts, but we're going to start keeping track of things in a little bit different way. It's going to be a little bit better, more conducive to writing equations. So I think I'm going to go straight into just giving you a few examples. So this is what, right here, this is what we call an LOL diagram. So maybe you can see why. This kind of looks like an L and this looks like an O. So one of my students a few years ago, when I make one of these up on the board, I start with this. And they're like, oh, LOL. And we all laughed out loud. And then we started calling him that. So that's just what I call him now. So let's read through these directions before. List the objects in the system within the circle. We are going to do that. And this little note, always include the Earth's gravitational field in your system. We are going to do that. We'll just put like EE for entire Earth. On the physical diagram, indicate your choice of zero height. That's important. We're just going to write like h equals 0. And sketch the energy bar graph, and I'll talk about that in a minute, what that means, and any energy flow in or out of the system. I'll explain what that means also, and then write an equation. Writing the equation part is really easy if you do the diagram right. So those are the steps that we're going to do. So here's an example. Let's say we have an object a ball, something like that, and it's dropped. So if we're dropping the ball, that means its initial velocity is 0, right? And then we're interested in an LOL diagram is always a diagram of like one situation or like one moment in time and then another moment. It's kind of like a before and an after. It is possible to do one that has 3 parts, like an LOLOL diagram, but we're not going to do that, at least not for a while. So here's velocity is 0 up at the top, and at the bottom this is just before it hits the ground. So it hasn't stopped yet, it's not bouncing or anything like that. Okay, so let's make our diagram. So first thing is what's in the system? Well, obviously the ball and the entire Earth. And there's nothing else that we have to, we're going to, in this one, we'll say we're ignoring air resistance. So in other words, if we were doing pie charts, we would be ignoring the dissipating energy. So let's do the pie charts. The pie charts would look like for ball dropped here, it has gravitational potential energy, and then at the bottom here it has kinetic energy, right? And we're going to say that here, this is the lowest it ever is. Of the 2 points that we're interested in, this is the low one, so we'll say that that's where the 0 height is. So I think we've done list objects in the system within the circle. There's the ball, entire Earth, so good. On the physical diagram, indicate your choice of the 0 height. I did that. And any energy flow into or out of the system. Energy flow into or out of the system would be either something that's like adding energy in from outside the system or something that's taking energy out. And I don't have that going on in this. I'll do another example where we have that going on in just a minute. Okay, so I think I'm good there. And now we want to make the bar graph. So basically the bar graph is just another way, instead of the pie charts, another way of indicating what's happening with the energy. So you can see, like when I give you an LOL diagram like these, you've got some choices here. There's your EK, there's your EG, there's your EE, there's your E dissipated. And notice that the E dis only shows up on this side. You're never going to have E dis like before things start happening. So I'm just going to put the EK there, like if you did have, like, or the EG rather, if you did have these ones in this problem, like there isn't any of those things at the start. There's not going to be any EE at all. So here on this side, this is like the before and this is the after. There's no EG anymore, it's all EK. And what's up with like the little like number of things here? I'm just doing that to indicate that it's the same number. Now there are some problems where it's going to like split up and whatever. So I think 4 is a good number to deal with, but it really doesn't matter. I'm just like making up some number. You could just have like 1 and then 1 here, whatever, as long as it's the same on both sides. 4 is a good number because we can kind of break that up and move it around as needed for more complicated examples. And then the last thing we're going to do is write in that little elongated box there where it says qualitative energy conservation equation. We're going to write that this EG is equal to EK. Right? Whatever the stuff is here is equal to whatever the stuff is here. That's all. All right. If you're thinking to yourself, you know, all of this, like making diagrams and putting things in the system and all that, like, come on, McGrath, I could just write that equation. Okay, fair. I think in this problem you could have just said, yeah, EG turns into EK, so that's it. But things do get more complicated, so bear with me and please try to understand these steps for making a good LOL diagram. So let's see, how about another example? Let's say we have, I'm going to do 3 examples for kind of a similar situation here. Let's say we have a ramp, and at the bottom of the ramp there's a spring, and we have a little cart here that's pressed up against the spring. And down here, its velocity is 0. It's pressed up against the spring, and then we're going to let go. And then in this one, we'll do our second position while it has not yet reached its highest point. It's still going up the ramp, and we'll say the velocity is, I don't know what it is, but it's greater than 0. Right? And while I'm doing my diagram here, I'm going to make this right here the 0 height, because that's when it's at its lowest point. Okay? So when it's here, then the height is, I don't know what it is, but it's some number. It would be greater than 0. So let's try to make our diagram here. In the system is the cart and the spring and the entire Earth. Why do we have to put that in there? Because of gravitational potential energy. That should be in the system. Okay? At the beginning here, do I have any EG? No, I'm at the 0 height. Do I have any EK? No, the velocity is 0. Do I have any elastic energy? Yes. All of the energy is stored in the spring right now. I'm going to make that 4 bars worth of energy. When I'm here, do I have EG? Yes. Do I have EK? Yes. It has not reached its highest point yet. And then do I have any elastic energy? No. The spring is done. Do I have any dissipated energy? Not in this problem right here. We're just pretending, let's say there's no friction. So I've got some EG and I've got some EK. Why did I do 2 and 2? Well, I'm just splitting up the 4. Does it mean those are exactly equal to each other? No, I'm just doing this qualitatively. This is split. You could do like 1 and 3. You could do 3 and 1. It doesn't matter so long as you're showing that this got split up somehow between these, and that you can then write your equation that says EE is equal to EG plus EK. Now, how about the same situation with our cart? And this time there is friction. And here it's compressed against the spring. This is the lowest it's going to be, so I'm going to call that the 0 height again. And then up here, let's say it's got all the way to its highest point. So the velocity is 0, and there is friction. Okay, that's the big difference for us here. And we're making our second point all the way at the top. So let's make the diagram and see what's different here. So what's inside this system? We are going to put the cart and the spring and the entire earth. And because there's friction, I'm also going to put the track in there. Right? So at the beginning, it's the same thing. I don't have any EG. I'm at the 0 height. I don't have any K. It hasn't been released yet, but I've got a bunch of elastic energy. So on this side, it's the same as what we did in the last example. And now here, what about here? Well, there is friction. So before I do anything else, if there's friction, we're going to have dissipated energy. How much gets dissipated? I'm just going to do 1 block. Right? Again, this is a qualitative exercise. You just need to somehow have the same number of blocks over here that you do over here, so we get the right equation. There's no EE. There's no EE because the spring is done. There's no EK because it got up to its highest point. So the other 3 blocks are gravitational potential energy because it's at a higher height now. The height is greater than 0. So what would the equation look like? EE is equal to EG plus E dis. 4 equals 3 plus 1. That's basically the idea. So we're just using these little diagrams, these little bar charts, to help us understand how to write these equations. And what about work? So what is work? Work is, as far as we're going to understand it with this kind of diagram, work is something that's outside of the system, either adding energy in on this side or taking energy out on this side. So what if I did the same as the last example, but I didn't put the spring in the system. So in here I had the cart and the entire earth and the track. The spring is not in the system. So if the spring is outside the system, then the spring is going to add, this is how I draw these. I go make a little bar with 4 little notches in it, and then make like an arrow showing that this is work done by the spring adding energy into the system. and that would be the same. Okay, now at this point you might be thinking to yourself, well, which one is right? They're both right. We are the ones, the universe just keeps doing what it's doing, regardless of whether we come along and try to write little physics equations about it. So it's just a matter of how we understand things and what we decide about what's in our system and what's not in our system. These two equations are going to accomplish the exact same thing. The energy stored in the spring and the work done by the spring, those are equal to each other. It's just a matter of whether we understand it as being like work done by the spring from outside of the system or the energy stored in the spring from within the system. The math is going to be exactly the same, and if we're trying to figure out some, how much energy was dissipated or whatever, once we get to the point where we have some equations, some mathematical models for these things, then we'll be able to do some stuff with numbers. So that's what it looks like when something is outside the system. If you're thinking to yourself, well, I'm just going to always put things inside the system. That's fine if it's up to you to decide, but I might tell you, something is outside the system, and that's just the only difference that it makes. It takes this and puts it here, coming in from outside of the system, because it's not one of these things. That's all. And then last example, just do one where I'm going to do it same as before. I should have written down here, same as that one, but the spring is not in the system, not in our circle. So this time I'm going to do the same as that one, but I'm going to put the spring back in the system, but the track is out of the system. So what does that do? I mean, the equation can't really be different. So it's a matter of calling something by a different name, maybe. So there's my elastic energy. Sorry, I should fill this out first. So I have my cart is still in there. The spring is back in now. The entire Earth is there. But I'm taking the track out. So instead of the energy being dissipated by something that's in the system, now we're going to have that friction. This is the going out. Here, there's my little arrow with the 4 bars. This is the work done by friction. So what's my equation? Oh, sorry, I messed that up. I totally messed that up, sorry. I forgot that we're up the ramp. I forgot which example we were doing. So I still have that, and this should be only 1 bar worth, 1 little block. So we're moving the block that was here to be an arrow coming out of the system. Those 3 are still there. So let me just, sorry, this is messy. Forget this whole thing here. I should have done, this is coming out on this side, 1 block like this. So there's my 1, 2, 3, 4, 1, 2, 3, 4. And if I were going to write an equation for this, that's the work done by friction, I have EE is equal to EG plus the work done by friction. And the work done by friction here, we just call it E dis. Now we're calling it the work done by friction. It's the same thing. That's all fine. That's all good. So what you need to know about the work coming in and going out is that we always have, if you have an arrow on this side, it is adding energy in. In other words, we never have an arrow on this side that's pointing this way, and we never have an arrow on this side that's pointing in. It's always flowing this way. There could be work coming in on this side, and there could be work going out on this side, and the other direction, not possible. I think that that's all I'm going to do for you here in the notes. And you go ahead and try, I think, as usual, go ahead and try the first one here, and then look at the video and kind of bounce back and forth with me, and we'll do it together. See you there.